This video is about inverse sine and inverse cosine. As always, read carefully through the textbook and take good notes, but now consider the following highlights in this video. Let's recall that we've already been working with some trig graphs, and we've defined and understood some of the basics of the sine parent function, or sine basic function. And in other words, if you have y equals sine of x, and we graph it on a coordinate plane, then we have our x-axis as the horizontal axis, our y-axis as the vertical one, and then we would recall maybe some basic characteristics of it, such as the graph does intersect at the origin 0, 0, and then let's just suppose we're looking at the right side of the y-axis for a second. We know that the period of sine is 2 pi, so we would expect that if you look at a span of 2 pi, so from 0 to 2 pi on the x-axis, you would see one full period of the graph of sine, and sure enough, it starts at 0, 0, it's then going up to its max value at 1, that would be the point pi over 2, comma 1, then it goes back downward, intersecting the x-axis again at pi, and then dipping below the x-axis, going down to a minimum value at 3 pi over 2. Of course, that min value is -1 at the bottom there for the y-axis, and then it goes back up until it hits again the x-axis, completing one full period of 2 pi. So we've talked about those details already. Of course, all of this is tied to the unit circle directly. We started with those special fractions, special arcs. That is all still very much in play. So the more comfortable you are with the unit circle, the better all of this stuff will be going, as you'll see. So as needed, keep writing it out, maybe a couple times a week, even every day if it still feels fuzzy, until that unit circle is very clear and easy to work with. Now, we're going to take a look more deeply at this sine function in order to understand its inverse. That's the topic of this video. And so this graph, that is the regular graph of sine of x that we just now kind of reviewed, this graph would not pass the horizontal line test. Okay, so this might involve putting your algebra hat on for a second to recall the horizontal line test. And this would mean that this sine function, just as is, would not be what's called one-to-one. You may recall that's the definition from algebra. In other words, it would not be one-to-one, nor then have an inverse that is a function. So we can restrict the domain of this sine function so that we are only using a portion of it which is one-to-one. This is just what's done in trigonometry for convenience, just to be able to work with an inverse function, which does matter. Since these trig functions are periodic, they just keep cycling over and over and over again forever. And because of that, it actually doesn't change a whole lot or matter if we cut down and focus in on one portion of it. So a convenient portion of this function to use, just kind of decided through the history of math, is the portion from negative pi over 2 to positive pi over 2. Now, we'll see why this is convenient to use here in a second. In other words, what we're saying is take the regular y equals sine of x, which we just kind of recalled, but cut it or clip it so we're only focused in where x is greater than or equal to negative pi over 2, but less than or equal to positive pi over 2. If you restrict the picture to that, then you're getting really just a portion of the sine function that on the left side stops at negative pi over 2, on the x-axis that is, and then at that left side of the boundary then, that's actually the bottom of one of the valleys. In other words, you're just clipping it at the point negative pi over 2 comma -1 at the bottom. And then, and it's inclusive because of the way we've defined this interval to be less than or equal to, greater than or equal to. In other words, there's a solid point there we're actually using. And then the graph would kind of snake upwards. It would hit 0, 0 in the middle, and then it would continue upward to the top where this would be clipped on the right side at the point positive pi over 2 comma positive 1. Okay, so what we're doing is just focusing in on a certain portion of the regular sine graph. That portion is defined where x, the input, is from negative pi over 2 to positive pi over 2. The range that we get as a result of that is also demonstrated here by the lowest and highest values being shown, so that you can see it goes from negative 1 all the way up to positive 1 vertically. All right, so we're going to, for convenience, use only that portion of the sine graph. Now, we could switch the x and y coordinates of every point on this graph segment to form its inverse. Again, going back to algebra, that's the rigid definition of an inverse. You just switch every x and y coordinate from a graph, and the new graph is the inverse. Now let's get a more formal definition for this sine inverse that we're going to be using here. So the inverse sine function is, now for notation, one way to write it is the sine name, so S-I-N, as we pronounce sine, but then the sine inverse would have what looks like an exponent of negative 1, but it's not an exponent, it's just notation for inverse. So it's called sine inverse, and it looks like a sine to a negative 1 power. Or another way to say the same thing would be, instead of sine inverse, you could also call it arcsine. That's just another name for the exact same thing. Arcsine means sine inverse. With domain negative 1 to 1 and range negative pi over 2 to positive pi over 2. And then before you get twisted around on those, hold on one second, because it will make sense here. Defined by the following: sine inverse of x is equal to y, which also implies that the sine of y is equal to x. Now note, as with any inverse functions, again going back to algebra, the domain and range are switched for sine and sine inverse. And you can tell by looking here at the definition for sine inverse, you'll see the domain is negative 1 to positive 1, and that was the range of the sine clip we were using. It goes vertically from negative 1 to 1, this little portion of the sine graph we're using. So now the domain of the inverse function is negative 1 to 1. And similarly, the range of this sine inverse function is negative pi over 2 to positive pi over 2. Now, those details do matter. We'll get into some practical use of them shortly with some examples. Here we're just kind of making sure the details are laid out for the definition. All right, so let's look a little bit more carefully at this graph for sine inverse. The graph of y equals sine inverse of x is as follows. Now remember, this graph can be obtained by switching the x and y coordinates from every point on the portion of the sine graph that we're working with here, which is simply from negative pi over 2 to positive pi over 2 for the x or input values. So if you take every point on that sine graph portion and switch the x and y coordinates and then replot them, you get this sine inverse graph, which then would result in the following. Notice for the sine inverse graph, you have a domain illustrated as the inputs, which go from negative 1 to positive 1. That's what we just said they should be. And then you have a range. Again, this is for the sine inverse graph. The range goes from negative pi over 2 to positive pi over 2. And these are inclusive intervals, meaning we are using the boundary points on these intervals for domain and range for this inverse function. that can be helpful to color coordinate this. So I'm going to highlight our x-axis, which we're now saying goes from -1 to +1. This is for our sine inverse function in a blue color. That's our domain. And then we'll use a different, maybe some kind of orange color for our range, which goes vertically from -π/2 all the way up to +π/2. And so this is all aligning or matching up with what we've just been saying about clipping a certain portion of the regular sine function, but then using its inverse, which would involve switching all the x's and y's. To bring something in from algebra, again, that you may or may not remember, but from the inverse function topic, we're going to note the following here, that sine and sine inverse, that is, those being inverses, can cancel each other out according to the following properties. Okay, so we have these summarized here, and we're going to be using these in examples shortly, but these are just the rigid definitional forms of these. So it turns out that the sine of the sine inverse of x would be x. In other words, the sine of the sine inverse, those would just cancel each other out. That's what it means. These are sometimes called the cancellation properties of the inverses. And so sine of sine inverse of x cancels, and that is for x being from -1 to 1. And then similarly, secondly, the sine inverse of the sine of x would be such that the sine inverse of the sine cancel each other out, and the result would be just x as well. But notice this time it's for x being from -π/2 to +π/2. And of course, these are all related to what we were talking about with domain and range above. As we do some examples shortly, you'll see why this matters and how it'll be used. And I think that'll be probably the easiest way to understand where these come into play. But for now, we're just going to kind of noting them with the definition here. And let's recall, the domain and range are switched, as we've been stating, for sine and sine inverse. Now, we can follow similar steps to understand inverse cosine. And since this video is on both inverse sine and inverse cosine, we'll just kind of flow right into inverse cosine next, which has a lot of similarity with what we just saw, which will help, I think, understand them. So, definition. The inverse cosine function is denoted cosine with a little -1 in the upper right superscript corner of it. Again, it looks like an exponent, but it's not an exponent. It's a notation for inverse. This is cosine inverse, or otherwise known as arc cosine, which would be spelled A-R-C-C-O-S, arc cosine, with domain -1 to 1 and range 0 to pi. Aha, notice now we have a difference in the range when you compare this with sine inverse. And so there's a reason for that, as we'll see just where it's cut for convenience. And this is defined by, oops, little typo here. This should be cosine instead of sine. I'll just rewrite this. So this should say, it's defined by cosine inverse of x equals y. So again, cosine inverse looks like cos with a little -1 exponent or superscript with it. So cosine inverse of x equals y. That is the same thing as saying that the cosine of y equals x. So those should say cosine there. Note, as with any inverse functions, the domain and range are switched. So this is true also for cosine. The domain and range are switched for cosine and cosine inverse. And then note, here's the convenience part, right? So for convenience, we trim the cosine function to use only the 1-to-1 portion of its domain, defined as 0 to pi. So this is different than it was for sine, but here's why this makes sense for cosine. If you think of the graph of cosine, it starts at the, if you go for the point 0, 1, like where it starts on the y-axis, let's say. So this one starts at the top of its hill, you could say, when x is 0. And then it continues to go downward until it hits a x-intercept in the middle, and then it goes down all the way to the lowest portion at the point pi comma -1. And if we cut it there, which is different from the sine function defined above, where we cut that one from -pi/2 to +pi/2, if we cut cosine from 0 to pi, the reason that's helpful is because you see the full range of values there from high to low. And so this is just what's done conventionally in math. We cut the cosine function from 0 to pi. And again, this will come into play as we do some examples shortly. As you'll see, this does matter, and we will use that portion of it. Thus, the graph for y equals cosine inverse of x is as follows. So again, if you just cut the graph of cosine as defined above from 0 to pi, and then switch every x and y coordinate in that graph, replot them, well, it turns out you get another graph. And this one looks as the following. So the domain for cosine inverse is going to be -1 to +1. Remember, that was the range of the cosine function, but they're switched now. And then the range of the cosine inverse function would be where we've cut it. So this would be from 0 to pi inclusively. Okay, so again, if we kind of mark this maybe with some helpful colors, you'll notice domain this time goes from -1 to +1, and then the range goes from 0 at the bottom up to pi at the top. And so you're getting a different slice than we used for sine, but it's the same idea. You're just cutting the original parent function and using only a portion of it. And then also note, just as it was true with the sine inverse function above, note that cosine and cosine inverse can cancel each other out. So let's note this. They can cancel each other out according to the following properties. So these would be the cancellation properties for cosine. They look similar to those of sine with some differences. So now cosine of cosine inverse of x, those cosine and cosine inverses cancel each other out, leaving you just with the x, and that is for x being from -1 to +1. Or similarly, the cosine inverse of the cosine of x, again, those inverse functions would cancel each other out when you're taking one of the other, leaving you with x for, this time, x being from 0 to pi, again, correlating with the cut we made for the portion of the cosine function above. And also recall, domain and range are switched. For sine and cosine, it should be, or sine and sine inverse should be cosine and cosine inverse. Okay, so they're inverse functions, which means by definition their domain and range are switched. Now let's move on and try some examples that will feel or get a little more algebraic in how we solve them, and you'll get to see now finally how we do need to use these restrictions on the domains for the functions that we use and then find their inverses that we've defined above for sine and cosine. You're going to see now how those matter and why they matter. So for some examples, we're going to find the exact value. Exact value means we don't want just some decimal approximation unless that is asked for. So we want the exact value of each expression if it is defined. All right, so the first example gives us a few to work with. The first one is sine inverse of 1. And it's written just like that. Sine inverse with a little -1 inverse notation there. And then of 1, meaning the 1 is just after that, implied as the input for the sine inverse function. Now I'm going to suggest a way that we're going to handle this so that we're writing down as much as possible to help us really understand what we're working with. It's tempting to try to do these in your head after you see how they're done, and it's dangerous not to write stuff down. So how we're going to do this is as follows. I'm going to take what we have as our original problem, given as sine inverse of 1, and I'm going to write y equals that. So really we're looking at y equals sine inverse of 1. And then again, the notation for sine inverse we're using is just the -1 superscript after the sine word, and then for the input of 1 after it, you may or may not see it written with parentheses, but if you want to be super clear, you can put parentheses after it. So we have sine inverse of 1. But I've set y equal to that, like the letter or variable y, which was not given in the original problem. But we're going to put it in there because it's actually really useful to do. Because now you'll see how these cancellation properties work, and you'll get to recall the properties for sine inverse that we're going to need, right? So let's recall that if y equals sine inverse of 1, then the range for this sine inverse function matters. What we can say is that y has to be between negative pi over 2 and positive pi over 2. So we're actually going to note that right in our problem. I'm going to write it next to our function, and it's probably logical to do as soon as you write the step of writing y equals sine inverse of 1, then directly to the right of that, this is where I'm going to just kind of note what we know above, which is that this y value has a restriction. The range of the sine inverse function is restricted based on where we've cut the sine function to produce it. And as we said above, you can review that above, the range for sine inverse, which we noted quite a bit above now. You can see the range above for sine inverse is negative pi over 2 to positive pi over 2. So we're just kind of bringing that back into the picture here, but it's important, as we'll see soon. So now notice what we're trying to find. The letter y we threw in just because we can, and it's convenient to find a variable to solve this expression or find this expression for sine inverse of 1. If I find y, I'm done. Well, what is y? I don't know. It's whatever the sine inverse of 1 is. Well, for convenience, we're going to do the following. We're going to apply some algebra. I'm going to take the sine of both sides of our function. So I'm going to take the sine of the left side of our function, which was just the y. And then I'm also going to take the sine of the right side of our function, as it was written in our previous step, which was the sine inverse of 1. And I'll try to use some parentheses here to hold things nice and snug. Okay, so then, and I'm going to color coordinate them too as well, because if I'm taking the sine of both sides of my equation, it's exactly that. My equation that I had at the previous step, which was y equals sine inverse of 1, now I'm just taking the sine of both sides. Okay, well, why would we do this? Well, notice what's happening here. If you look at the right side of what's now our equation, you have the sine of the sine inverse of 1. But what happens with the sine of sine inverse? Well, if you look at our cancellation properties above, those cancel out. And that's the convenient purpose of taking the sine of both sides. So now, what does that leave us with? Well, on the left side, we would have just the sine of y, which is what we had at the previous step when we took the sine of it, or took the sine of both sides. On the right side, the sine and sine inverse cancel, leaving us just with 1. So now what we're wondering is, the sine of what would equal 1? Right? That's what we're wondering, because we want to figure out what y is. Y was what we set our original expression equal to. So the sine of what is 1? That's our question, which is really just a unit circle question. So what I'm going to suggest is that we just bring in or redraw a very brief and mini unit circle just to remember it. Now again, if this is like super fresh in your mind, you may not need to redraw it. Or if you're doing an exam, usually students will redraw it at the beginning completely and then not have to keep redrawing it. So that would be fine to kind of refer to as well, but let's just kind of bring it back in here. When is the sine on our unit circle equal to 1? Remember, the sine is the y-coordinate of any of the terminal points. Well, it's only equal to 1 at one place, and that is the very top of the unit circle. So let's just kind of recall and note that at the top of the unit circle, the sine value is 1. Now, what would take you there? Well, what arc would get you there? Starting at 0 on the right side, that would be, as you may recall from our unit circle, that would be where y, the input arc here, would be pi over 2. That's like 1/4 of the circle. It's the first top right, kind of moving through that first quarter of the circle. And if that is a length, an arc length of pi over 2, which it is according to our unit circle, then that's the value that would take us where the sine is 1. So in other words, the sine of pi over 2 is 1. Now again, that's really just a unit circle question that you can get by glancing back at the full unit circle. The question we need to figure out is, does that y value fit within our restrictions that we've noted here? So note that we have to have y between negative pi over 2 and positive pi over 2, and turns out that inclusively, and it turns out that pi over 2 does actually fit. So since it's within the range for sine inverse that we've had to use for our y value, we can say comfortably that that is our answer for finding y, which was the variable we set equal to our original expression. In other words, we got the original expression. Now let's apply the same kind of reasoning and thinking to do our next example, which would be like 1b here, and we want to find, for this one, the sine inverse of root 3 over 2. So for convenience, we're going to use this same trick where we take that original expression and set it equal to y. So I'm going to say y equals sine inverse of root 3 over 2, and then directly next to that we're going to recall that because y now is the output value or the result of a sine inverse function, then y has to be within the range of sine inverse, which, to remind us, it's a good habit to write it out, that means y must be between negative pi over 2 and positive pi over 2. So we have that restriction for y. We'll see why those restrictions can matter here eventually, but we're noting it here just to get in the habit of it and help us memorize that. We have y equals the sine inverse of root 3 over 2. Well, just like we did before, we're going to take the sine of both sides this time. So I'm going to say sine of the left side, which was just the y, equals sine of the right side, which was this sine inverse of root 3 over 2. And again, the whole point of taking the sine of both sides is that now we can use the cancellation property. And so on the right side here, our sine of sine inverse will cancel. And what that leaves us with is the sine of y on the left side is equal to, well, root 3 over 2, which is all that's left on the right side after those sine and sine inverses cancel. And this is, again, back to a unit circle question. So refer back to your unit circle or sketch another one briefly. And we want to find out where the sine value is positive root 3 over 2. So again, you can refer back to where this happens. Sine values are positive in quadrants 1 and 2. So we're stuck in those. And we want positive root 3 over 2. That could happen in a couple places, actually. One would be in the upper right zone, quadrant 1. And another place that sine is positive root 3 over 2 would be the symmetrically same place on the quadrant 2 location, so upper left. Either of those are where sine is positive root 3 over 2 according to our unit circle. Or you could say, like, we have two candidates for our answer here, right? It could be positive pi over 2. Let's just kind of write these down here. Not pi over 2, pi over 3. That's one possibility on the quadrant 1. Or if you went all the way over into quadrant 2, the other possibility would be 2 pi over 3. So we'll say here we have pi over 3 or 2 pi over 3, which would take you to the second option where the sine value is positive root 3 over 2 in quadrant 2. But we have to now refer back to our restriction, which we've already noted for convenience here. So since we know that the y value we're getting here, the output of our sine inverse function, has to be stuck between negative pi over 2 and positive pi over 2, only one of those two options is, right? That's like saying it's got to be somewhere in quadrants 1 or 4. And so obviously only one of our points is there, which means that tells us which one is our valid answer. So y equals, in this case, pi over 3 as our final result. In other words, we exclude the 2 pi over 3 because it just simply does not fit within the range we have for our y value, our sine inverse output. Okay, there's a lot of detail and it's easy to get twisted, maybe even overwhelmed at this point. But if you keep rewatching, trying on your own, practicing and practicing, practicing, it will start to fit together. These are just applications of all the definitions we've been building together so far. So we'll just make note of that. I'll just say that this 2 pi over 3 possibility is not in our original restriction for y, so we'll just put a little frowny face there to say can't use it because of that. And that's why, again, the range of sine inverse does actually matter and should be memorized, but with practice it will be, because it means you're kind of focusing in on what the actual solution here is according to that cutoff for the y value. All right. Our third example begins as sine inverse of sine inverse of 2. We want to evaluate sine inverse of 2. Well, let's do the same thing we've been doing, which is, I'm going to rewrite this. I'm just going to kind of slide to the right and do this here. I'll say y equals sine inverse of 2. Now, we know that that has a restriction with it, and so we need to note that it's the same one we've been using. So let me just say here that negative pi over 2 less than or equal to y less than or equal to positive pi over 2. That's the restriction on y as the output value for sine inverse, coinciding with everything we've been doing above. So we just have to keep that in mind. Same thing from the previous examples. However, in this case, when we take the sine inverse of both sides, so now we have, again, y equals the sine inverse of 2. If I take the sine of both sides, then I would have the sine of y on the left side equals the sine of the sine inverse of 2 on the right side. But, okay, same things are going to happen here. The sine and sine inverse will cancel out. What we're going to see next is that you're left with the sine of y on the left side equals 2 on the right side, right? Because the inverses cancel, leaving us just with the number 2. That's the same thing that's been happening in the examples so far. Problem is, when does sine of anything equal 2? The answer is never. If you go back to the original tried and true sine function, it's recalled above and in previous lessons, the sine value has a maximum of 1. It's like saying, when would a terminal point on the unit circle have a y value of 2? The answer is never. The highest it goes is a positive 1. So because of that, we would actually have to say that there's no solution to this, or you could say it's undefined. There is no value y such that sine of y equals 2. So it's undefined. All right, let's move on to our next set of examples. For number 2, we're going to work now with some cosine expressions. And so 2a begins as cosine inverse of negative 1. In other words, we want to evaluate we want to find the exact value of that. Well, same trick we've been doing for the sine inverse expressions, except now we're using cosine. And what will that change? Well, it'll change, you'll see, the value for the range of the y. So we're still going to use this trick where we take the original expression and write it as y equals. I'm going to say y equals cosine inverse of negative 1. And when we do that, we're going to immediately note what the values of y could be. In other words, the range of cosine inverse. So refer to this back above if you'd like. We have our cosine inverse function defined here previously, and the range was from, well, 0 to pi. Remember, that was cut differently than the sine function. So that means in this expression, we're still going to say y equals cosine inverse of negative 1, but now what we'll say is that y is greater than or equal to 0, but less than or equal to pi. That's where that function was cut. And so same process, just different portion of it now. And then the next part we'll do is the same thing. I want to take the cosine of both sides. So I'll say, let's find the cosine of the left side, which was the y. But now we're taking the cosine of it. And that means we'll also take the cosine of the right side. So let's see, cosine of, on the right side, we had the cosine inverse. So we're taking the cosine of the cosine inverse of -1. That's what we had there. But if I take the cosine inverse of it, which I'm denoting in a different color here to help coordinate or visualize this, what happens is we end up with the cancellation property. So on the right side, cosine of cosine inverse of -1, those cosine and cosine inverses cancel each other out, which means what we have left all together on the left side is cosine of y equals -1. The only thing left standing on the right side after those cancellations. So again, this is just kind of a unit circle question at this point. We'll bring one back in play and wonder when. This is almost, there's not a whole lot of work to show when you get to the unit circle because it just matters on whether we know the unit circle. So the question here is the cosine of what will give us -1? Well, again, the cosine is the x-coordinate of all the terminal points. When is the x-coordinate -1? It's only at one spot. It's at the far left side of the circle. So the question is, where is that? Well, it kind of depends where you start and which direction you go. Let's remember that we're talking about values between 0 and pi. So that would mean like 0 on the right side of the unit circle, and then pi is on the left side all the way around. So halfway around the circle, going in a counterclockwise direction, halfway would be all the way up to pi. So one possible answer would be pi. Now you could also say that -pi is an answer, but we care about which ones are within our restriction for y values here. So according to the unit circle values we know, if y is equal to pi, then the cosine of pi is -1. And again, what matters is that that is within the restriction we have on the y value as the output of the cosine inverse function restricted from 0 to pi. Pi is within that because it's an inclusive boundary, which means we can say pi is our exact value. The y equals pi, which means our original expression, which is what we set y equal to, is pi. Okay, moving on to our next one. To the right here we have cosine inverse of 1/2. Same process, let's walk through it. We're going to set that as y equals cosine inverse of 1/2. Of course, we'll immediately write the restriction on y, the output for the cosine inverse. Same thing as before, y has to be between 0 and pi. If y is an output for cosine inverse, that's the range of cosine inverse. And that means then if we take the cosine of both sides of this, we'll have the cosine of y on the left side equals the cosine of the cosine inverse of 1/2. But then the cosine of the cosine inverse will cancel, leaving us with the cosine of y equal to 1/2, which is now onto a unit circle question. When does the cosine value equal 1/2? Again, the cosine is the x value. We're looking around the terminal points of the unit circle to know when does the x value equal positive 1/2. Well, you'll find a couple places that it's positive 1/2. One of them is in quadrant 1. That would be where the input is pi over 3. And one of them is in quadrant 4, where you could say the input is 5 pi over 3. Or negative pi over 3, same thing. But what we care about next is which one of those fits within our restriction for the y value in this problem. And what we find is that actually only one of those does, so the positive pi over 3 actually does fit within the restriction for y, which has to be between 0 and pi. And so since that one fits, we'll use it and say that for our answer here, the y value must be positive pi over 3. And again, that means that would be the input for cosine that gives us a 1/2, going back to the unit circle. And thirdly, for another cosine inverse example, we're starting here, for example, 2c with cosine inverse of negative root 3 over 2. So same process we're going to follow here. It may start to get a little routine. That's a good thing. We're going to say y equals our expression. So y equals the cosine inverse of negative root 3 over 2. And we'll immediately write the restrictions we know for y on that. We'll say that y has to be between 0 and pi. Again, that's just coming directly from where we've already restricted the range of cosine inverse, which is related to where we cut the cosine function in our definition above to get us a one-to-one function. Okay, all that stuff is coming into play right here. And it matters because sometimes, again, it reveals which of the possibilities you get is the actual solution, as we've been seeing. So now let's take the cosine of both sides of this, which will give us that the cosine of y is equal to the cosine of the cosine inverse of negative root 3 over 2. And again, using our cancellation properties here, the cosine of the cosine inverse on the right side, those will cancel. That means on what we have on the left is just the cosine of y equals, on the right side we just have negative root 3 over 2, which is again back to the unit circle. Sometimes sketching one real quick is a helpful reminder, or again you may have the whole thing already kind of resketched with you on your exam, just sitting there waiting for you to use it. We want to find out where is the x-coordinate on one of those terminal points equal to negative root 3 over 2. Well, you may find a couple places because of the symmetry, and negative root 3 over 2 is going to be in quadrant 2 or 3, so like the left half of our unit circle graph, and it's like the points that are kind of further out toward the left side, closer to the x-axis. One of them would be 5 pi over 6, that's the quadrant 2 option. The other one would be 7 pi over 6, that's the quadrant 3 option. And so the next question is, well, which of those falls within our restriction on the y value? If you're going from 0 to pi, you're stuck in quadrants 1 or 2, which means one of those will work. And so that's the one we'll use. So this happens to be 5 pi over 6, the one in quadrant 2, which means we'll say here y equals 5 pi over 6. And remember, y is what we set our original expression to, which means that's the value of our original expression. All right, let's keep working through some examples. In this next set, we're going to use a calculator to approximate the value of each expression to 5 decimal places. All right, so we're using a calculator here by request or instruction. And we have 3 of these expressions. The first one says sine inverse of 2/3. Now, we're not going to go through all the process of writing y equals and then taking this sine of both sides. I mean, you could kind of walk through those same steps that we just were doing, but the values this time are not nice unit circle values, and that's kind of the point of using a calculator. So rather, what we're going to do is just punch these in, and if you take out your graphing calculator, I'm going to demonstrate how you can get through this or do this. So let's start by turning on our TI-84 Plus calculator. When you turn it on, we're going to first check the mode, and we'll do that by hitting the mode button in the upper left corner. If you press mode, you want to look down. I think the third row of options should be what you need here. It has to be in radian mode. It should either say radian or next to it might say degree. That's because you can do either mode, but we're working with radians so far, and so we're going to keep it in radian mode. If you have it in degree mode, it will give you the wrong result. So make sure it's in radian mode. which you can do by going over radian with your cursor and just hitting enter. Once it is, we can just go back to the regular screen by hitting second and the quit feature or second mode button. And then we're just going to type this in pretty much as we see it because the calculator has this function on it. If you notice, likely, I mean, the colors may be different on a different calculator, but usually there's a button in somewhere middle region that says sine, and of course cosine and tangent are next to it. And then above the sine button will be usually in some kind of color sine inverse. It has a little inverse notation. So on my calculator, if I hit the second button and then the sine button, it goes up to that sine inverse feature, which is exactly what we want. So notice in the screen it will put in SIN with a little -1 superscript. That's our sine inverse notation. Then it gives an opening parenthesis, after which we want to put the input value for this example, which is given as 2/3. So I'm going to put in 2 divided by 3, and then importantly, close the parentheses. So the input for our sine function is the 2/3. That's now, hugged or closed within parentheses. That's what you need. Now we're going to hit enter, and as long as we're in radian mode, it will spit out a value that is the approximate decimal value we're looking for. And of course, these instructions said to round to 5 decimal places. So according to what our calculator showed me, that would be approximately 0.72973. So 0.72973 is the rounded to 5 decimal places value the calculator gave us. Okay, so we'll do some more of these in the same kind of way. The next example says the cosine inverse of -3/7. So take our calculator back out. This time to get cosine inverse, it's the same kind of thing. We're going to hit second and then the cosine button. And as the input, we'll put in -3 divided by 7 for the -3/7. Again, close parentheses after the input. It's important to do that. And then hit enter. And the output here looks like 2.01371 if we're going to round it to 5 decimal places. So let me write that down. For B here, the approximation is 2.01371, and that's the approximation for cosine inverse of -3/7. Okay, and then thirdly, we have the cosine inverse of 1.23456. Okay, now if you've been really paying attention carefully above, you might already notice something going on with this input value. This is suggesting that we can put the input of a cosine inverse function as 1.23456. That's not actually a valid input. So if you go back up and review the domain and range of cosine inverse, you'll recall the domain of it is restricted from, well, -1 to +1, because that's the output restriction on the regular cosine function. Okay, so that's all kind of tied together above. Let's though see what the calculator shows us if we try this, just to be familiar with it. If I go back and type in the same way, second and then cosine to get the cosine inverse, and then I put it in here 1.23456. I mean, you don't even need that much detail. If it's bigger than 1, you're going to have a problem, or less than -1, same thing, right? If I hit enter, notice what happens. Error domain. Okay, so the calculator knows that's not a valid input for cosine inverse, and it's not going to give you a result. So we'll just call that undefined. Or you could say there's no solution. Okay, for our last set of examples in this topic, we're going to find the exact value of each expression if it is defined, but this time we're going to have nested trig functions, one with an inverse maybe of itself. So, for example, example 4a says we want the sine of the sine inverse of 3/2. Now, I'm going to suggest a process that will get us through this, I think, carefully enough, and that is we want to start focusing on the inside of the first set of parentheses. So you'll notice it was sine of, sine inverse of. Well, let's just look at what's inside the first set of parentheses. That was the sine inverse of 3/2. if we were to treat that inner portion like the problems from a previous set of examples, let's see, it was set, I guess, numbers 1 and 2, the first ones we did, then watch this. If we call that inner expression the letter y, and then just say that y equals just the inner portion, sine inverse of 3/2. Remember what we did above if we were trying to find what y is there? We want to find out what just that inner portion is first. Well, you may already kind of see it, but if not, try the same thing where we take the sine of both sides of this equation now. So I'm going to say this, if I take the sine of y, I'll get 3/2. If I take the sine of both sides, then the right side, the sine and sine inverse would cancel. So I had sine of y equals 3/2. Well, when does that happen? The answer is never. 3/2 is beyond the range of sine, just like we saw in that previous example. So since that will never happen, let's see, I'll put a little frowny face here. That's not going to happen. There's no solution. The sine of anything is never 3/2. That's beyond the range of sine. So for that reason, we would have to say that this overall example is undefined. Or again, you could say there's no solution to it because there is no value such that y or sine of it is 3/2. So that inner portion is undefined. And if the inner portion here is undefined, then the whole problem is undefined. Okay, well that's kind of a special case. Let's look on to another one. Example B says cosine inverse of cosine of 5 pi over 6. Well, we're going to follow the same process, and on any problem like this, and you'll see plenty of them, it's best to work from the inside out. So we're going to do the same thing. If I look inside this first set of parentheses, what I'm looking at there is the cosine of 5 pi over 6. Well, as soon as you write that out, what do you notice? Notice that we know what that means, right? If you go back to the unit circle, 5 pi over 6 is in quadrant 2. So if you imagine your 3 special places, 5 pi over 6 is the one in quadrant 2 that's closest to the x-axis. And we know what the cosine value is there. It would be negative root 3 over 2. So that's just, again, directly from the unit circle, nothing magical there. Of course, you have to have the unit circle pretty memorized or close by for that. But if that's the case, again, that's just from the unit circle, then what we're really working with here is the cosine inverse of what we just said, which is negative root 3 over 2. That's what that input was. So let me color coordinate this. We're talking about this value being what the cosine would be at 5 pi over 6, and that's what's the input of our cosine inverse function that we started with in this problem. Now, okay, pause for a second, just look at this and look back a second. This is exactly what we were dealing with in a previous set of problems, right? You're starting now, well, kind of restarting, I guess you could say, with an inverse trig expression. We have the cosine inverse of negative root 3 over 2. We want to figure out what that means or what that represents. Well, that's exactly where the problems up in examples 1 and 2 were starting, right? We started with, well, specifically example 2 had the cosine in it, right? Cosine inverse of whatever the input was. So that's now exactly where we are. We're going to use the exact same process to go from there. I'm going to let y equal this. So cosine, y equals cosine inverse of negative root 3 over 2. If I take the cosine of both sides, I have the cosine of y equals negative root 3 over 2. Of course, it's always good to write out the restriction as soon as you hit this step. So what we did above was say, as soon as we wrote y equals for our expression, which we just do for convenience, we should also write the restrictions. The cosine inverse would leave y restricted from 0 to pi. And we noted that above in all those examples. Again, this is kind of referring back to the same thing as example 2 we did above, which had a, b, and c with it. We're really just doing the same kind of problem now. So I'm looking for where does cosine on the unit circle equal negative root 3 over 2. Now, conveniently, you'll notice we just kind of did or dealt with that in the previous step here. So where does cosine of y equal negative root 3 over 2? It's at 5 pi over 6. And so we can say comfortably here that y must be 5 pi over 6. Now, okay, if you're thinking carefully on, and yes, that does fall within the restricted values. We're good there because it's between 0 and pi. If you're wondering why we didn't just, okay, fair question, why didn't we just cancel the cosine inverse and the cosine? Well, you actually could have, but that does require you to recognize or remember, if you go back up here, okay, what we said was, if you go back high enough where we were defining cosine and cosine inverse, we said that those cancel with the cancellation properties as long as you keep in mind the restrictions. And so if you keep those in mind, then you can just cancel the cosine with the cosine inverse. But if you forget those restrictions, this process we just went through is an easier way to remember them, okay, or not forget them. That's why I might recognize or recommend going through this full process, even though it ends up seemingly trivial. Like, couldn't we just have canceled the cosine inverse with the cosine? Well, it turns out we could have. I just wanted to make sure it's clear on why. And if it wasn't, if they didn't fall within the correct boundaries, that would become evident as you're writing out the restriction on cosine. So this process, I think, is actually helpful. And speaking of it, let's do another one. The next one is given at the beginning as sine inverse of sine of 5 pi over 6. So again, we're going to start on the inside and work from the inside out. On the inside, we have sine of 5 pi over 6. We'll go to the unit circle, find 5 pi over 6. It's the third special place in the quadrant 2, closest to the x-axis. And what's the sine value there? Well, it turns out it's 1/2. So we could say this. We're really looking at the sine inverse of, really it's just 1/2. That's what the sine of 5 pi over 6 is. So we're looking at the sine inverse of 1/2, and the question is, can we do that? The answer is yes, but let's be careful to follow our same process. So I'm going to introduce the variable y. Again, this is exactly what we were doing above. Again, in those previous or initial examples, I'm going to bring y and say y equals sine inverse of 1/2. Why do we do that? Because that reminds us that we have restrictions on y. And as long as we have these memorized, it's really helpful, because what we know is that the output for sine inverse, which we're calling y, has to be stuck between negative pi over 2 and positive pi over 2. And again, that's just from directly above in our initial notes defining the sine inverse function, and based on where we had to cut the sine function to produce it as a one-to-one function. All that stuff, right, it does matter, and if we remember that, then we can go, okay, fine, we have a restriction on what y could be. Why does that matter? Because where would sine equal 1/2? Well, it's actually in two places. You're looking at in the quadrant 1, the first place where we have the first tick mark, again according to our unit circle, and then also quadrant 2 with a third tick mark. In each of those cases, you have places where the terminal point has a y coordinate of positive 1/2. And that's relevant to what we're working with in this problem. So the question is, does it matter which one we use, or should we use both of them? The answer is it does matter, and it's based on this restriction. So remember, we have to let y be stuck between negative pi over 2 and positive pi over 2, and only one of our options is. That is the quadrant 1 option, which would be actually pi over 6. So what we'll say here is y equals pi over 6. And I'm going to put an extra note. I'm going to say here, just for reference, not 5 pi over 6 because of the restriction that we have above. We couldn't use the 5 pi over 6 because it's not within the range of sine inverse, which we recalled in that portion of our step directly above. So 5 pi over, or sorry, so pi over 6 is it. That's our final result. And lastly, let's do the following: cosine inverse of cosine of 17 pi over 6. Okay, well, we're going to follow the same process here and work from the inside out. So on the inside of this one, we have this cosine of 17 pi over 6. Now that fraction might immediately make you a little nauseous or like, oh great, we have to work with this ugly fraction. It's not horrible. Let's just recall that we can figure out what that means. If you go back to the unit circle and just recall that it keeps lapping or overlapping itself as you go bigger than 2. So 17 pi over 6, let's convert that as a mixed number. That would be 17 over 6 is really 2 and 5/6, right? This is just using some arithmetic to get this fraction in a more user-friendly form. 17 pi over 6 would really be 2 and 5/6 pi, right? Because 2 and 5/6 is the same as 17/6. Now, if that's the case, I just got to figure out where that lands us on the unit circle so that I can know what this inner value represents. If I start at 0 on the right side, that is 0 as an arc length, and then I go around one full circle. Remember, that would be a full 2 pi. So I'm trying to go 2 and 5/6 pi, which would take us 5/6 more than that, which would take us all the way around to what is the same thing as 5/6 pi originally. And that's the place we're looking at. And what I'm trying to find is the cosine of that. And the cosine there is the x value, which would be negative root 3 over 2. Might be helpful to illustrate this with a spiral as we did early on with the unit circle. We went around one full circle, and then we went all the way around another 5/6 to end up where we are now, which is what this function was given as the input for here. So now really what we're working with, I'll just rewrite this. This means we're working for, or trying to find the cosine inverse of that inner part, which we know now represents negative root 3 over 2. Right? That's what it would be on the unit circle according to this terminal point where it would end, right? So negative root 3 over 2. Now let's use the same thing we've been using above, which is I'm going to set y equal to this. So y equals the cosine inverse of negative root 3 over 2. That should immediately, or hopefully with practice, trigger our remembrance of the restriction on the range of cosine inverse. Remember, this was where y would have to be stuck between 0 and pi, the range of cosine inverse. And if that's the case, we're just going to go to the unit circle and figure out what option works for us. Because if I take the cosine of both sides, I'm really looking for where the cosine of y would equal negative root 3 over 2. On a unit circle, there are two options for that. Negative root 3 over 2 would be one of the two places that's closer to the x-axis in quadrant 2 or 3. And we're looking for which of those, of course, falls within our restriction of 0 to pi, which happens to be basically quadrants 1 and 2. So only one of those does, which means that's the one we'll have to use, which means we can say for our final result that we have y equal to, in other words, the cosine of what is negative root 3 over 2? Well, the cosine of 5 pi over 6 is that. And so that's our output value. That was the one we could use because it fell within our range of cosine inverse. So you can see how all these details do fit together. And I think doing the problems about the same way every time is actually helpful because it gives you a pattern and kind of a predictable process to follow that gets familiar.